Yeah, welcome back everybody to our Pacific Quasiworld seminar. So I hope you all had a good summer. So we will continue our seminar series here as usual in the middle of the month with two talks. So let's get started here for our first speaker today. So this is Giulio Tiozzo from the University of Toronto, and he will talk about open dynamical systems, geometry dynamics, and thermodynamic formalism. So please.
Thank you. Thank you for the invitation, especially Mario, Chen, Mitsu. And yeah, it's a little late here in Toronto, but I'm still awake, so let's keep going. So what I'm going to talk about is this sort of long project that I've been working on, especially with Tushardas, Mario Urbanski, and Anna Zdunik. And this is about general open dynamical systems and their thermodynamic formalism. And in fact, we're even writing a book on it that is almost finished. So you will hopefully enjoy it at some point soon, before the end of 2024. But of course, yeah, the first goal is to define what is an open dynamical system, which basically just captures the idea that you have a dynamical system and you cut a hole in the space where the dynamical system is defined, and then you look at all the trajectories of the points that don't fall into this hole. This is the general idea. And I will start with some history and, of course, first earlier results about things about the Hausdorff dimension, for instance, of objects related to this open dynamical systems. And then I will discuss the new material. And as you will see, there is a lot of functional analysis, for better or for worse. So brace yourself. Okay, so this is a book. So what is the simplest dynamical system that I'm sure you're all looked at? It would be the doubling map on the circle. So you just consider 2x mod 1. And this, of course, is a very well-behaved system. We know a lot about it. But one thing to make things more interesting is to cut a hole in the circle. So you fix a number t from 0 to 1. And we look at the interval 0 to t, and we think of this as being a forbidden interval. So if you think of this as a forbidden interval, what you do is you define a set, which traditionally it's called the surviving set, which is the set of point x, such that if you iterate under the map G, you never lie in this forbidden interval from 0 to t forever. And clearly, this set depends on this t, so on the interval that you've chosen. And of course, you would expect, since the system is ergodic for the Lebesgue measure, of course, such a set would have measure 0, but maybe it will have some interesting dimension, for instance. And so the question that we ask in general is, for instance, how does this set, surviving set, changes as you change in this parameter?
So can I ask a quick question?
Yeah.
So it seems that actually for most t's you get the empty set, or
no, only if t
no?
is if t is bigger than 1/2, you get the empty set. Yes.
Oh, I see. So okay.
Yeah. So t is kind of small, but not super small. You will see. I'll draw pictures. In fact, yes. So okay, basic properties would be that this is decreasing with the parameter because you're increasing the hole, so the remainder is decreasing. And indeed, if t is bigger than 1/2, it's empty. Actually, maybe just a 0.0. And also, interestingly, this set is forward invariant for the dynamics, obviously not backward invariant, otherwise you would get the whole interval. And so one thing that I started looking at already a few years ago was the Hausdorff dimension of the surviving set. And you can draw the picture, and you can see that as t equals 0, you still have the whole set. So the dimension would be 1 on the left. And as t equals 1/2, you don't get anything. So clearly it's 0. Could you please tell us a bit about what motivated you? Yeah, I'll come to this later, because for me this was a toy model for studying problems in complex dynamics, like the entropy of real unimodal maps, and actually even or even the core entropy for complex polynomials. So this is the toy model, so to speak. You just take the doubling map, the simplest possible dynamical system. But this problem is older, as you will see. So the other thing you will see from this picture is that, well, this function is decreasing, but it's not strictly decreasing. There are places where the function is locally constant.
Yeah, I was actually going to ask about this, if I may interrupt.
Yeah,
so
very
do you
much so.
exactly know where these plateaus are? And
yeah, for this particular function, yes, and it is very, very cute. And there is a very nice combinatorial description that I can tell you later, but this will be a different talk. But yes. And then the other thing that we really are interested in is, again, this is not really a smooth function, but you can look at the, for instance, the Hölder exponent of this function, see whether this function is Hölder or not Hölder or something like this. And so here's so first question is, how does this vary as a set? And second question is, how does the dimension vary? So this is a whole problem. In fact, Urbanski, maybe even in his master's thesis or something, he proved that this dimension is continuous in the parameter. And in fact, these plateaus where it's constant have full measure. And he already gave some, and this for this particular model, it's relatively straightforward. I mean, the computations are not really hard, but still, there are interesting phenomena. And many more people studied these open dynamical systems in a much bigger generality for expanding maps and things like this, where the whole gets small. So the whole at some tends to zero. And for instance, Keller-Liverani proved that this function is differentiable at t equals 0 for this particular function here, and many more things. What is the asymptotic behavior near 0? And then there's many people that Bunimowicz, Yurchenko, Detman, Demers, and many others that studied much more complicated systems, like billiards and things like this, where you remove a small hole. And again, you're interested in this asymptotics when the hole gets to 0. But what we're interested in is not so much when the hole gets to 0, but just at every possible scale. So, and also there's an obvious relation with the topological entropy, because you have this Cantor set, KT, which is forward invariant, so you can define the topological entropy. And you have the classical formula that, you have the dimension of this invariant set times the Lyapunov exponent, which is log 2 in this case, gives you the entropy. So this is a linear map, so it's not so complicated in this situation, but it will get more tricky later. And then another quantity that people looked at, which we will very much interested in today, is the so-called escape rate, which is, instead of looking at the points that never escape into the hole, we wait until time n, and we ask for the points that don't escape in the first n steps. And this set has some measure, it's not 0, the measure, but this measure will get smaller and smaller as you increase the time. And so this growth rate of this quantity, we call it the escape rate. And in fact, in this model is easy to show that this is very, very precisely related to the dimension of the surviving set, because you have this relation, eta equals 1 minus r over log 2, so very precise. And then another thing that you can relate these things to is various forms of Diophantine approximation, because it's a little bit like a shrinking target problem. So for instance, in this particular situation, you can think of like, you have numbers between 0 and 1, and you want to approximate it with dyadic numbers. And then, so if you define the set of points that are, not very well approximable with dyadic numbers, in this case, only on one side, because the whole is just one-sided from 0 to t, not on the other side, then you also get a very not so complicated to prove relation between these quantities in Diophantine approximation. So these are various perspectives on this system. Are there any questions so far? Okay, so again, so now let's look at the first the variation as a set. So as a set, sometimes it could be that you vary the parameter and the set doesn't change. This happens, and this is very much related to these plateaus that we saw. And so we call U the set of bifurcation parameters, which are the parameters for which indeed the set does change locally. And in fact, there is a pretty cute characterization of this bifurcation set, which is also in terms of some sort of open dynamical system in a sense. Like you look at the parameters t such that for the orbit of the doubling map, they never fall into the hole between 0 and t. So that's a parameter space version of the definition of KT that I had before.
So your definition of bifurcation parameter looks like opposite. The set is stable in a neighborhood.
The bifurcation parameter is, oh, sorry, is the opposite. Yeah, you're right. Sorry, yes. If it's not stable in a neighborhood, yes. Sorry. Yeah, sorry. Yeah, I guess there should be not equal. Sorry. Yeah, you're right.
Or does not exist, epsilon.
Yeah. Sorry. You're right. And anyways, and obviously this shows immediately that the set has 0 Lebesgue measure just by ergodicity of the doubling. And you can say many more things about these plateaus using this characterization. Now, let's go back to the Hausdorff dimension. So the most important thing that we look at is the local Hölder exponent. So obviously, if you have a function, you can ask what is the best local Hölder exponent for it, meaning that the obvious Hölder estimate works for the exponent eta or anything just slightly smaller than eta. And what is really notable about this function, which I proved in 2016, is the following: that if you exclude these parameters where the function is locally constant, for any other parameters, the local exponent of this function equals the value of the function at the same point. So a way to think about it is that, yeah, so for instance, if the dimension is 0, the locally near where the dimension jumps from 0 to non-zero, the function is not locally Hölder. For instance, at t equals 1/2, the function is continuous, but it's not locally Hölder. But as the function grows, you get towards 0, the function gets more and more regular. And in fact, not just vaguely, but precisely, you have this estimate on the nose of the local Hölder exponent at each such point. So if you think about this picture, maybe you can get more of an idea what happens, that, if you see that if you're going to the left, the function sort of gets more and more regular, the oscillation of this function gets smaller and smaller, and in fact, when you're at 0, basically the function is almost almost differentiable, basically, and it's 1 plus epsilon Hölder. And then okay, any questions about this setting? So as I said, this was for me and Carlo, this was the more like a test case for something more, I don't want to say more interesting, but yeah, for us at the moment it was more interesting, which is entropy in complex dynamics. So in fact, it turns out that if you look at the topological entropy of real quadratic polynomials, so you look at the family f of z equals z squared plus c and say c is real, you can parameterize that both as a function of c, or you can parameterize it as a function of the external angle, meaning as the angle of the external ray that lands on c in the Mandelbrot set. And if you do this, you get a function that is very, very similar. And this is the classical Milnor and Thurston entropy function, which was again proven by Milnor and Thurston to be continuous and monotone. And again, this function has more or less the same properties that I said before. In fact, it is locally constant on certain plateaus. And these plateaus, in this case, are related to renormalization in the quadratic family, so to small multiple sets. And then what I proved in 2017 is that there is exactly the same relation, and I think this was not known for this function, is that there is exactly the same relation between the local Hölder exponent of this function and the value of the function. So even in this case, what you do is you look at a small neighborhood of a parameter, and then you look at the best local Hölder exponent, and this best local Hölder exponent of this function equals, in this case, equals the value of the function divided by log 2, because again, you always have to divide by log 2, and because entropy divided by Lyapunov exponent is the interesting quantity, which is basically between 0 and 1. So this would be a longer digression, so I don't want to talk more about this, but this is indeed another motivating example. So another thing to realize is that, if you want to compare this with the classical differential equation that we all studied in school, that, you want a function that is equal to its derivative, well, then there is a unique one, which is the exponential function. If you replace the derivative by the local Hölder exponent, then indeed there is no uniqueness. There are many functions that have this property. In particular, you can look at, instead of the doubling map, you can look at the tripling map of the circle and so forth. So you get countably many such examples. And the same asymptotics is true. And also, if you look at the topological entropy of real polynomials, this function is similar to this dimension function for the doubling map, but it's not the same function. However, this is also related to an open dynamical system, but yeah, it takes a little bit to set it up, so I will not do it. Okay, so that's sort of the historical and motivational perspective. Are there any questions? Okay, so now let's go to a general setup. So what we set up to do more recently with Anna, Tushar, and Mariusz is to understand more or less the general theory of open dynamical systems. And the general theory starts with having a continuous map of a metric space. And you can have an open set in your parameter, in your phase space. And once you have an open set, you can look at the surviving set again, looking at all the points such that under forward iteration, they don't fall into the hole forever. And again, you are interested in studying geometric and dynamical properties of the sets. And similarly to before, you also have a notion of escape rate. Of course, it's not obvious that this limit even exists, but similarly, usually you have a natural measure on your space X, and then you look at the set of points that does not fall into the hole for the first n iterates, and this is a certain measure, and you look at this measure, how fast it decays. So these are the most important objects, and obviously the most typical case would be you take a point psi, and you look at the metric ball of some radius, and you take that as your forbidden set, and then you look at the surviving set. And so you can look at, for instance, the Hausdorff dimension of this surviving set as a function of this radius, or the escaping rate in this for this open ball, again, as a function of the radius, and see what kind of dependence do you have. Do you still have this Hölder dependence? Do you still have continuous dependence and things like this? And in fact, indeed, more precisely, you can study the modulus of continuity. So in general, we're going to take some epsilon and some r. So epsilon will be some parameter that tends to some parameter r. R need not be 0, and you want to look at this modulus of continuity of these quantities. This is the general setup. So far, it would be just for any metric space. Of course, it would be really, really very general, but we'll see. Okay, and then, so what kind of space? So in fact, this famous book will have 2 volumes. So in the first volume, we concentrated for most of what we're doing on just the symbolic settings. So we're looking at the shift space. Then I will tell you a few applications that are not on shift spaces, but the most important system which we're looking at will be just some sort of shift of finite type, but on a countable alphabet. So this will allow for many general situations, for instance, the Gauss map, or whenever you have a first return map, usually you need countably many symbols to parameterize it. So it's fairly general. So you would have a countable set, which is an alphabet, and a sort of matrix that tells you the transitions that are allowed and not allowed. And so you would have some infinite words that are admissible, whether if every transition between consecutive symbols is allowed. And so, okay, this is the classical setting. We look at admissible words of certain length, EAN, or we look at infinite admissible words, and then we have a notion of cylinder, which is given a word, the set of infinite words that start with this finite word. So one condition that we need for our system is to have some primitivity condition, and in this countable setting, instead of having a primitive matrix like in the finite case, we say the following: that there is a finite set of words of the same length. So there's some length p and some finite set of words of the same length, such that whenever you have 2 symbols, I can start with the first symbol and then attach one word in this finite set, and then I can attach any other symbol. So this concatenation between I, W, and J is also this. So this is the correct definition of generalization of what is a primitive matrix. And of course, for us, the dynamical system of reference at this level would be just the shift on the set of infinite words. So this is sort of the classical. Okay, and what are the functional spaces that people look at? Well, the most classical one for shift spaces is the space of Hölder continuous functions. So how do we define Hölder in this situation is, well, you look at the cylinders. So you look of length m. So you look at all the set of infinite words that share the prefix of length m. And you look at the oscillation of the function over a cylinder of depth m. And this is a function. And then what you want is some Hölder continuity property, meaning that the oscillation over cylinders of length m is bounded above by some theta, which is some constant less than 1 to the n. So this is, again, pretty classical. The only thing which is slightly not completely classical is that this definition only tests every cylinder of length at least 1. So it doesn't compare points that are not in the same cylinder. So in particular, it does not imply that the function is bounded. And however, we have another condition, which is the summability, which means that, e to the supremum of this function over every cylinder is a convergent series. So of course, then this would give you boundedness if you have this. Okay, so this is the classical setup going back to Bowen. And if you have this, then you can define the topological pressure for this shift map in this symbolic space, which is, of course, a generalization of the entropy. If phi equals 0, you just get the topological entropy, or in general, you look at the growth of this function phi. And so, for instance, very classical theorem due to, in this form, Molding and Urbanski, says that if you have this finitely irreducible system and you have this summable one-cylinder potential, there is a unique important measure, which is called the Gibbs measure. And Gibbs measure means what is written here, that the measure of a cylinder of length n is comparable with this quantity in the denominator of the exponential of Sn phi. Sn phi is the Birkhoff sum minus n times the pressure. So means that the measure of the cylinders somehow decays in a controlled way, which is somewhat controlled by the iterates of the behavior of this function phi and its iterates. So again, this is the classical definition that everybody in thermodynamic formalism uses.
So sorry, a quick question.
Yes.
Can you go back to the formula? So where do you evaluate S and phi? At any point in the cylinder?
Yeah, that's right. Yeah, I mean omega. Yeah, let's say that you evaluated omega, and then in the numerator you have the nth cylinder that contains omega. Yeah. Okay, and in once we have here, well, to study, we're interested in studying statistical properties of the systems. So the usual important operator that people studied is the so-called Perron-Frobenius operator, which is somewhat a dual operator to the Koopman operator, which is just, taking a function and decompose it with the dynamics. And dually, you take a function and you look at all the preimages, and then you sum over all the preimages. So the function is G, and then you kind of sum over all the preimages, and then you weight them by this e to the phi, or this potential. Again, this is all classical. I'm not inventing anything new here, and what is very nice about this setup, again, this is quite classical, is that if you look at this Hölder continuous bounded functions, this Perron-Frobenius operator preserves this set of functions, and it's quasi-compact, and it has a very nice series of spectral properties. Under this primitivity assumption, indeed, it has a strong spectral gap, meaning the following, that there is a unique leading eigenvalue and leading eigenvector. So the leading eigenvalue is this exponential of the pressure, and the eigenvector is a unique up to scaling, and so we call it rho phi. And basically the rest of the spectrum is well contained inside the disk of radius e to the pressure. So you have one leading eigenvector, so you have a one-dimensional projector onto that, and everything else has spectral radius which is strictly smaller. So in particular, if you start iterating this operator with the sum function, you will converge to this function rho phi. And dynamically, this means that, this rho phi is the density of an invariant measure. So basically, dynamically, this would correspond to the fact that if you start with some point and you or some observable and you iterate, you will converge to this invariant measure. And so in particular, the fact that you have this spectral gap tells you that all the good mixing properties are satisfied. So you have not just mixing, but exponential mixing, so exponential decay of correlations, and this gives you the central limit theorem, law of iterated logarithm, and so forth. So all that you can possibly want is true in this setup. Are there more questions? Am I going too fast? Okay, so this is for Hölder functions, and this again is well known. The problem is that when we're studying these open dynamical systems, the situation is not very good, for this functional analysis, because if you now we consider some open sets, but this open set can be quite wild. It's not a union of finitely many cylinders. It's just some very bizarre open set. For instance, a ball. Let's say a ball, but the ball is for another metric, not a ball for the nice metric. And so what is natural here is to consider this adapted Perron-Frobenius operator, where you take a function g and you multiply by the characteristic function of the complement of u. So the set where you're not falling. However, this is very bad from the point of view of Hölder functions, because of course, this characteristic function is very much not Hölder continuous. It's not continuous to begin with. And so that is, creates a lot of problems, because then even if the function phi is nice, once you throw in this hole, you destroy this Hölder property. And so here you need the first new idea. And the first new idea, as maybe you could guess in this situation, is to come up with the new Banach space. Of course, the trick is it's not always easy to find the right Banach space. Okay, so what is the Banach space in this situation? Well, in this situation, is this space that we call the Keller BMO space. So BMO space means bounded mean oscillation. So these are somewhat well-known spaces in analysis, and this is a variation of it due to Keller, but I don't think he used it exactly in the same context. So it's kind of new. Okay, so what do we do here? We have a measure. We consider a version of oscillation over cylinders of depth m, but just essential because there's this measure. So up to measure 0. And then what do we do? So in the Hölder function definition, you take the oscillation function and you take the supremum of it. So you take the L infinity norm. But here, instead, we take the oscillation function and we take the L1 norm. And we want this oscillation function to decrease also exponentially with m. So we take some theta, which is less than 1. We take this oscillation function, we take its L1 norm, and then we multiply by theta to the minus m. And so obviously we want this quantity to be finite. If this quantity is finite, then we are happy. So basically, for every theta less than 1, one can define some space like this of the functions that have this sort of controlled oscillation in the L1 norm. And then, okay, to make it a nice Banach space, you also add the L1 norm. Okay, that's not a problem. And yeah, and this you call the Keller BMO space. So what is nice? There are many things which are nice. First of all, this is also an algebra, because the norm of a product is controlled by the product of the norms. And also a very important point is that the inclusion of this space inside the space, the L1 space, is a compact operator. So the image of a bounded set is relatively compact. And this is absolutely essential to get this good spectral property. And so now now this is the function analysis. How about the geometry? We have to say something about this geometry. So the good condition for the geometry is what we call the thin boundary holds. So, okay, maybe here it would have been nice to have a picture, but I can draw a very rudimentary one. Let's see, maybe. See if I manage. So okay, so basically what you do is you consider your grid of cylinders of a certain depth. So of course, as n gets larger, you get a finer and finer grid. So you consider your grid, and then you look at your hole. And then what you do is you define the boundary of this scale. So let's say that, the hole is something, I don't know, something like this. something like this. Then you take all the pieces that intersect the boundaries. So not the ones that are contained and not the one that contain it completely, but just the boundary parts. So something like this. Okay. So for each n, there is such a thing. And now what is required is that the measure of this nth approximation of the boundary goes down exponentially fast. And if this is the case, we call this a thin boundary. And that's the nice situation. And in fact, this is the key observation using this norm. If U has thin boundary, then the characteristic function of its complement indeed belongs to this interesting bounded mean oscillation space. Now,
sorry to interrupt. A quick question. If the set U is a cylinder itself, or finite union of cylinders, does it then have thin boundary for reasonable measures?
Yes. Yeah, then the boundary would be empty at some point after finitely many. Yeah.
Oh, I see. It would be empty. Yeah, I see.
Yeah. This boundary eventually would be empty because this is really this joint union of cylinders. So yeah. That's right. So that's the in fact, if that's the case, you don't need this very new Banach space. In fact, this case was already analyzed by Ferguson and Polycott, and they already do these things. But that's why we need. Yeah.
So okay, have you thought about like a question in the non-symbolic case?
Say it again.
Have you thought about a similar question in the non-symbolic case where you do have boundary?
I'll let you know later in the talk. Yes. So the answer is yes, but yeah, it gets complicated. But yes.
Yeah, usually.
Yeah. No, but there are conditions. Okay, so for instance, in this case, you do get everything that you had before. No, I guess I should clean this drawing. Yeah. So indeed, you get a nice spectral decomposition using this different Banach space. And indeed, you get the usual facts that you have a leading eigenvalue, leading eigenvector, and a spectral gap. And so from the point of view of stochastic properties, this dynamical system is really, really nice. Everything has exponential decays. However, this is only for one hole. Now, what we are interested in is not just one hole, but you have a one parameter family of holes. So for instance, you want to change the radius of the ball. Right? And so this leads to the second difficulty, which so we have this general definition, which we call perturbative scheme. So we consider some parameter space. So usually it would be just the interval, but it could be more exotic. So just topological space where we have a marked 0. And for each parameter, we associate a collection of open subsets. So we have a measure metric space, and you have a collection of open subsets, and there is some continuity. Okay, well, U of 0 would be empty, okay? And then we want that the measure, the symmetric difference goes to 0 as the one hole tends to another. And we also want some uniform control on this thinness of this boundary. So we want that the boundaries are always thin and uniformly so as we are changing this hole. So this is the notion of perturbative scheme. And okay, examples. Okay, the easiest example would be if you just have a ball in Rn and you take the Lebesgue measure. Of course, the boundary, there's no boundary. The boundary is measured 0. There's not much of an issue there. But what is more tricky is but what is kind of interesting is that you, in fact, basically in every in almost every situation where you have a coding, so suppose you have E infinity, so you have a symbolic system and you have a coding map pi to some metric space, and you have some measure on it, and suppose that you know that the measure of the ball of radius r is upper bounded by r to some power. Then in this situation, you can tell that there is not every ball will be part of this nice perturbative scheme, but if you allow to throw out to say 1% of the parameters, then all this you would have a set of parameters of that forms a nice perturbative scheme, and this would be completely general. Of course, in specific situations, it would be even. I mean, you can check more nicely depending on the situation, but it's kind of curious that if you allow, if you want to throw some small percent of the parameters out, you can basically do this in every metric space, which is kind of curious. Okay, so that's the definition. Now, what is the second problem? The problem is that if you look at this B theta norm, if you look at the Perron-Frobenius operator and you ask whether there is a continuous dependence, the answer is no, unfortunately. So even if you take a ball that converges to some other ball and you look at the difference of the two Perron-Frobenius operators, and you measure in this B theta norm, this is not continuous. Yeah. So this is quite annoying, as you could. So again, what is the solution? Once again, to introduce yet another Banach space. And in fact, again, this is also an idea that comes often in thermodynamic formalism, is to endow your space with two norms, one stronger and one weaker, and then look at some special operator norm where the norm on the target is not the same as the norm on the range. So in fact, you can define this weak norm. So this is a little tricky because you have to look at all the, you have to look at this set U, you look at its M boundary, and you look at all its preimages. So and you look at the integral of this G on this preimages. So it seems a little complicated, but fortunately, in the good cases, we can still control this norm. And this norm is weaker than this B theta norm. And in fact, the trick, as I said, is that you have two norms, one strong norm, which we draw in red, which is the norm that we look at in the domain. So we look at an operator, and we take the norm of L of G, we take the weak norm of L of G over the strong ball in the domain, right? So we compare the norm of G with the norm of L of G, but we use two different norms. Again, this is kind of a standard trick, which, for instance, was used already by Keller and Liverani in their perturbation theory. And we're going to do exactly the same, but in this case, we're going to use these two new norms. And so once you have this new operator norm, then fortunately, you do have good continuity properties. And indeed, you have this lemma that, okay, I'm not going to discuss it too much in details exactly what are all the terms, but the idea is that if you look at the unperturbed operator L phi, and you look at this operator L phi U, where U is this open set, then you measure the difference between these two operators in this funny norm. Well, this can be bounded somehow by a term which has to do with the boundary of U, which we know is thin, and also the measure of U, which again, as UR goes to U epsilon, basically, you have the difference of the measures, and so somehow this will converge to zero. So this is the secret somehow, and as a corollary, it does tell you that this operators in this norm behave continuously as a function of your radius. Any questions? Okay, so now I have, I guess, another 5 minutes. So I'll try to conclude and let you know just some very basic applications. I mean, I think there could be really many applications of the setup, but so far we just worked out a few. So first of all is in this setting, you can prove convergence of escape rates. So once again, you have this hole and you look at the escape rate. And what you know is that for each hole, for each radius epsilon, there is an equilibrium state or a Gibbs measure on the surviving set. So you look at this potential and you look at the restriction of the potential on its on the surviving state, on the surviving set, and there is a unique equilibrium state. So it satisfies the variational principle, and then this is the measure that is naturally associated to each such surviving set. So for each epsilon, there is a measure. And so the point is, if you have a perturbative scheme, so this is quite general, and you have a family, again, of these open sets, and we know that the escape rates, first of all, exist, because it's not obvious that even the limit exists. And then you know exactly how their modulus of continuity behaves. So if you go from epsilon to R, and you take the difference of the escape rates, this converges like at the same rate as mu R of the difference between the two sets. So you can think of U epsilon being like a ball, and U R is a smaller ball. So in the denominator, you have an annulus, basically. And mu R is the measure on this annulus given by the parameter R. So this gives you a precise scaling law for the modulus of continuity as a whole approaches another whole. Of course, this is still quite abstract. So let's see, maybe in slightly more geometric terms, what could be some applications of this kind of statements. So, okay, so for instance, now suppose we have a compact metric space and we have a topologically exact and distance expanding map. So topologically exact means locally eventually onto, that every open set after finitely many steps is mapped on the whole space. Distance expanding in this case literally means that if you have two sets, 2 points that are close to each other, the map is really expanding locally. And then you take a point psi, which is not periodic for this expanding map. So this is not in the symbolic setting, because in this case we know that there is a Markov partition, so there is a coding that you can put on the system, and then you can use that. And in this case, you look again at the escape rate for this family of balls, and as epsilon varies, again you have a precise scaling law for for instance, if the ball epsilon goes to 0, you know that the escape rate converges as the same rate as the measure of the ball of radius epsilon. where mu phi is the natural equilibrium measure for this potential.
So this is an analog of this differentiability result that you mentioned, right?
Yeah, that's exactly right. That's exactly right. Yeah. And in fact, as a final application, let me tell you an even closer analog, which is for so in particular, yeah, let me just say, okay, this you can replace, you don't need to have just one map, but you could have several maps forming, so organized in a graph. So this is called the graph-directed Markov system. So you can have transitions that are allowed, transitions that are not allowed. So like iterated function systems, things like this, and still you would have similar setting, similar result. But if you want to look at Hausdorff dimension, then you need to require the system to be conformal. So in that case, you would have that you do have geometric potential, and in particular, this geometric potential will be Helder, which is the reason why you need this conformal. For instance, if you look at expanding maps of the circle, again, you can take an expanding map of the circle. You could take a point which is not periodic, and you can look at balls of radius r around that point. And again, you in this case, you can replace the escape rate literally with the Hausdorff dimension of the surviving set, because the system is conformal. And you see that you have, for every parameter, you can estimate the modulus of continuity of this Hausdorff dimension, and you estimate it with the measure of this annulus. So AXI R epsilon is an annulus. And so mu is the surviving equilibrium measure for the correct potential in the correct dimension. And in fact, kind of as a sanity check, you can realize that, you know, if you take the equilibrium measure for the geometric potential on on S1, well, this gives you an absolutely continuous measure. So measure which is absolutely continuous with respect to the Hausdorff measure in the right dimension. And so this is just a measure of the annulus with respect to the correct Hausdorff measure. So obviously the measure of the annulus is rescales rescales in the correct way. And so this this gives you the you know, it's the same setting that I was talking about at the beginning. Okay, so that's the end, I think. So I'll just leave you with a picture of the 4 authors. Thank you for your attention.
Okay, thank you very much. Let's thank the speaker. And yeah, let me start the discussion. Mitsu.
Yes. So what in what you are doing? Where was the plateau? So what's how the plateau comes in your talk?
In this more general setting, or in the original setting?
Or today's talk. So sometimes in your pictures at the beginning, there were plateaus. So where this set doesn't change or dimension doesn't change.
That's right.
And so how do you see in your result?
Yeah, I think, yeah, exactly. Yeah, there is this setting that, so first of all, you have this non-periodicity of the point. So I mean, when you have a plateau, the endpoints of the plateau are periodic points.
Mm-hmm.
Yeah, and then, okay, depending on the situation, yeah, basically, let me see.
It's probably hard to find an analog in this super general setting, right?
Yeah, but so yeah, I think you have certain non-degeneracy condition that is is true in the plateau. I mean, the plateaus will likely exist in other settings. The thing is, what could happen in general, what the phenomenon that usually happens is that if you're moving your radius, you sometimes the set really does not change. The surviving set really doesn't change. So by what I was considering in, for instance, in this original case of the plateau, this would be ball centered at 0. So zero is definitely periodic for
yes,
right?
yes.
But if you consider
so that's excluded the case.
So yeah, so we exclude the center being periodic, and I suspect that this might rule out the plateaus. But it's a great way. Yeah, I haven't thought too hard about this, but I think that might be the case.
Do you mean that if the center is not periodic or not periodic, then the plateau doesn't occur for these
I would expect so, actually.
I see. Okay.
Yeah, it's a good remark. I had not thought about it in this way, but I strongly suspect. Yeah.
Okay. Are there other comments or questions?
So maybe I have a question. So in your symbolic set, so first of all, is the first book archived, or can we find it somewhere?
It's not archived, but yeah. Now we are doing the proofreading. So yeah. So really, you can buy it.
Where is
No,
available?
I mean, we are. It is really. We have a contract, and it should be really out in a couple of months. I mean, yeah, we're doing the proofreading. So
okay. What about the second book? What's the content of
Right. So the goal, yeah, basically the first book is to do all the setup in the symbolic setting. And then the content of the second volume would be to, do the applications. And so then it would, and then there should be lots of applications, including to, rational maps, including to expanding maps, multimodal maps, all this stuff.
For the second volume?
Sorry?
You have a schedule for the second volume? When can we see it?
But I don't want to give promises. Maybe end of 2025 would be reasonable for the second volume. Yeah.
I see. Now, for what you talk about on the symbolic case, when you remove a ball, in a symbolic case, do you still have a symbolic, relatively simple symbolic, system, or you really, or mess up the combinatorics?
No, that's the problem. The combinatorics is pretty messed up, right? I mean, so the idea is exactly that you start with a very nice system, like doubling map or anything like really expanding and Markov. But then when you remove this ball, since the ball does not respect the Markov partition at all,
right?
That's where it's really complicated to that. I mean, again, a special case of this, I can show the secret slide. Is that in the complex dynamic? I mean, you get all the real Giulio sets, right? That's a special case, right? So if you look at the doubling map, and I look at the interval from theta to minus theta, so across 0, and then I'm looking at the points that don't return there. This is literally the Hubbard tree for a real quadratic polynomial.
Okay, thank you.
So as a special case, you get at least this complicated, and I'm sure in higher dimension it would be more complicated. Yes. Yeah.
Thanks.
Okay, so we are running out of time here. So let's thank Giulio again.